Section 3.3, the chain rule. The objective of this section is to find the derivative of a composite function using the chain rule. This is a new differentiation rule that will be applied to find the derivatives of composite functions. So just a quick review of what composite functions are. Suppose I have the function g of x, which is x squared plus 1, and I have a function called h of x, which is, for instance, the square root of x. In algebra, we've studied that we can put one of these functions into the other one. So for example, if I want you to put the g of x function into the h of x function, I would write something like h circle g of x, and this is basically saying put the function g of x inside the function h. So in other terms, you're supposed to take the x squared plus 1 and plug it into the h function wherever you see an x. And this will result in the square root of x squared plus 1, since the original x gets replaced with the g function. So in this section, we are going to be given things like this, and sometimes they'll be called, for example, f of x. So let's say f of x is the square root of x squared plus 1. The question is, what is the derivative of this function f of x? And the way we find the derivative of this f of x is by using this new rule called the chain rule. Now, to simplify things, we have a couple of different ways to state the theorem. We'll start with the basic definition, or the basic way it's defined, and then we'll have a special case that we'll describe down below that will help us with the majority of the problems we'll come across in this course. But starting with the general chain rule, we're told that if we want the derivative of a function y, and the function y is a function called f of u, so it's got some inside part and it's got some outside part, and we want to differentiate it. According to the rule, what we're supposed to do is find the derivative of the outside function first, then multiply by the derivative of the inside function. Now, to make life easy, we're going to call the inside function u, and the outside function will be called f of u or whatever. So in this particular instant, back to the problem that we started, the inside function would be the x squared plus 1. This rule uses the letter u to describe that portion. And the outside function would be the square root of the u that's inside. So let's kind of practice how to use this notation. And like I said, this is for general problems, but in our case, in this course, we will be restricted to very simple or very specific type of problems. So you will have a different way to find the derivative for those types of problems, and it's in the bottom of this page in that second theorem. So in any case, let's pretend that you come across the function y equal to x squared plus 3x minus 4, all raised to the power of 7. They want us to describe the inner function. So what would be the inner function if I have this in my problem? So we can see inside the parentheses the quantity x squared plus 3x minus 4. That's the base that's being raised to the power of 7. So in this particular problem, we can say that the inside function is actually x squared plus 3x minus 4. Sometimes we call it g of x, sometimes we call it u. So it doesn't matter what we call it. The inside part is x squared plus 3x minus 4. That's the u of the problem. Now, if I decide to call x squared plus 3x minus 4 by the name u, what would be the original problem rewritten? So that's what they're asking us in part 2, to identify the outer function. So the outer function, we can see that there's a power of 7 on the base x squared plus 3x minus 4. So we've already decided that x squared plus 3x minus 4 is called u. So then the problem can be rewritten as u to the power of 7. So in other terms, the outside function, which now depends on the variable u, so that's why we're calling it f of u, is u to the power of 7. So far, basically what we're doing is we're breaking down the original problem. We're identifying the inside part and the outside part. So a quick way or an easy way to identify the inside and outside is to think to yourself, if I plugged in a number inside this function, for example, if I plugged in x to be 1, then what's the last thing I have to do in the problem? So if I plugged in the 1, for example, I would have to start by squaring the 1, then I would have to multiply the 3 and the 1, then I would have to subtract 4. And when I'm done doing all this, the last thing I would do is raise it to the power of 7. So raising to the power of 7 is therefore the outer function, and everything else you did would be considered the inner function. So the squaring, multiplying by 3, and subtracting 4 would be considered the inner function. So that's one easy way to identify the outside and inside function if you are having a hard time doing that. Now that we found the inner and the outer, we need to apply the chain rule to find the derivative of the original problem. So suppose I ask you for the derivative with respect to x of the original problem, which we're calling y in this case. So in other terms, I'm asking for the derivative with respect to x of the quantity x squared plus 3x minus 4, all raised to the power of 7. So what does the rule tell me to do? The rule basically tells me to do this. It says, first, differentiate y with respect to u, then multiply that by the derivative of the u with respect to x. So what are all of these pieces? What is the derivative of y with respect to u? So to find this part over here, we go back to the second part of the problem, and we say, what's the derivative of y with respect to u? So in other terms, what's the derivative of u to the power of 7? Well, the basic power rule tells us to do 7u to the power of 7 minus 1, which is really in reality just 6. So that's the first part that needs to be written down. So in other terms, down here, I would write down 7u6 to begin with. Then I need to multiply that by the du divided by dx, meaning the derivative of u with respect to x. So where do I get this guy from? Well, I get it from part 1 of the problem. We already know that u is x squared plus 3x minus 4, so what is the du divided by dx is going to be? What is the derivative of x squared plus 3x minus 4? Well, again, the basic power rules tell me to differentiate the x squared to get 2x, then differentiate the 3x to get 3, and then finally the derivative of 4 is going to be 0, so I'm not going to write it down. So according to the theorem, that 2x plus 3 needs to be written after the product down here. So 2x plus 3 gets multiplied with 7u to the power of 6. Now, obviously, we don't like that answer because it has two different letters, two different variables. So the last thing in the problem is to usually rewrite the answer with the variable that we started the problem with. So in this problem, we started the problem with y's and x's. So we want to write down the answer in terms of x. So from all this, we can say that the derivative of y with respect to x is 7, but u was really in reality up here, x squared plus 3x minus 4, and it needs to be raised to the power of 6, and then we multiply it by 2x plus 3, which was already there. So this is the general chain rule, and this works no matter how complicated your problem is going to be. Now, like I said earlier, in our course, we are restricted to very specific types of problems where we can use what's known as the general power rule. So the general power rule that we're describing down here is a special version of the chain rule. It turns out that the chain rule can give us the answer to many more problems that we don't need to see in our course. So we are going to create a brand new rule called the general power rule that can help us solve problems like the one we just finished doing much faster. And when I come across problems like this, meaning I have a certain base like parentheses or whatever, all raised to the same power, I can use this general power rule. And the general power rule works very similar to the simple power rule in the fact that you're supposed to drop the power to the front, subtract by 1, so that's the first part. Then you find the derivative of the base and you multiply the answers. So if I wanted to do this problem again using the general power rule, I would say, well, wait a second. It looks like I have a certain base raised to the power of 7. So according to the general power rule, I'm supposed to drop the 7 down and subtract 1 from it. And in this moment, leave the base alone. And when I'm done doing all this, I need to find the derivative of the base and put it on the side. So derivative of x squared is going to be 2x, derivative of 3x is going to be 3, and derivative of 4 is just 0, so we don't write it down. So this gives us the same answer that we spent a lot of time finding, but using the special version of the chain rule that we're calling the general power rule. The part 2x plus 3 over here at the end is called the derivative of the inside. So you'll see me or you'll hear me say many times throughout this video and later on in the course that I'm multiplying by the derivative of the inside. What I mean by that is I'm multiplying the original problem by the derivative of the inside stuff that was raised to the power of 7 in this problem. Okay, so let's practice the chain rule and specifically the general power rule in the following next few problems. So we're told in example number 2 to find the derivative of each of the following, and we have multiple parts. So let's begin with the first one, which says y equals to 3x minus 4, all raised to the power of 5. So technically, the inside part is the 3x minus 4. The outside part is the function that raises to the power of 5. But I'm not going to use that notation. I'm just going to go straight into the general power rule. So according to the general power rule, if I see a base raised to a power, and in this case, the base is not just regular x, it's 3x minus 4, what do? Well, I pretend for a second that it says x. If I had x to the power of 5 and I wanted the derivative, what would the derivative be? Well, it would be 5x to the power of 4. So I would write 5, but instead of x, I would write 3x minus 4 to the power of 4. And since my base was not regular x, I'm going to multiply the answer that I just got by the derivative of the inside. So the 3x minus 4, what is its derivative? Well, it's just simply 3, because the derivative of 3x is 3 and the derivative of 4 is basically 0. So now that I've found this part, all I have to do really is just multiply the 3 and the 5 to get my final answer. So the derivative with respect to x would be 15 times the base 3x minus 4, all to the power of 4. So it sounds fancy, but really it's like the simple power rule with an extra little step at the end where you have to multiply by the derivative of the inside. So this part, the 3, is the derivative of the inside, and the inside part is the 3x minus 4. We find its derivative, we put it on the side, and don't forget, you gotta multiply. So even if the problem doesn't look like that, you can rewrite it sometimes to be like a base raised to a power, and that's what we're dealing with in part 2. So in this case, we have the square root of 6 minus x squared and the cube root of 4x plus 3. Both of these look like radicals. So before I begin the problem, I'm going to rewrite the problem as 6 minus x squared with power 1/2. So where did the 1/2 come from? We have an invisible power 1 on the 6 minus x squared base, and there's an invisible 2 on the radical. So that's where that power 1/2 came from. This is a rule that I've mentioned before in the past. If I have the nth root of a to the m, this is the same thing as am divided by n. So if you don't know this rule yet, it is time to finally memorize it. You will need it multiple times throughout this problems, because if you don't know it, then you'll have to rewrite the problem using this notation that we described over here. And I think that's more complicated than just knowing a simple rule to rewrite the problem with radicals. So using the same rule, I can see for x plus 3 inside the radical, the second radical, and I need to give it some kind of power. So again, the inside power here is 1, it's invisible, and the outside power is already 3. So I can rewrite that part as 1/3. And remember, this is not the derivative yet. This is just me rewriting the problem so I can use the chain rule. As a matter of fact, we have to use the chain rule twice, one time for the first base and one time for the other base. So let's do this. So finally, time to find the derivative of y with respect to x. And so again, I'm going to pretend like there's an x base right here. It's raised to the power of 1/2. So if I'm using the power rule, I would just bring the 1/2 down, then subtract 1 from the original power. By the way, 1/2 minus 1 is really just negative 1/2, so I'm going to write that instead. But remember, the base was not x, it was 6 minus x squared. And because of that, because the base is not just regular x, I'll need to multiply by the derivative of the inside, the derivative of the base. And keep in mind that derivative of 6 is 0, and the derivative of x squared is just 2x. But 0 minus 2x is really negative 2x, so let's just write negative 2x for simplicity. Now there was a plus next, so I'm going to put that next and differentiate 4x plus 3 to the power of 1/3. So again, I'm thinking like I have an x right here raised to a power 1/3, so I need to drop the power down, then subtract 1 from the 1/3. And by the way, 1/3 minus 1 is really negative 2/3, so let's write that instead directly. And now we think to ourselves, well, the base used to be 4x plus 3, and that's not just a regular x, so therefore I need the derivative of it on the side. So I multiply by the derivative of 4x plus 3, which is just simply 4. And so that's because the derivative of 4x is 4, derivative of 3 is 0, and 4 plus 0 is just really 4. And I'm going to leave it like that as 4. So at this point in time, I've found the derivative, but all I want to do in the next few steps is just make it look prettier, make it look better by combining, for example, this 1/2 and this negative 2x, and this 1/3 and this 4, and maybe I'll stop there. So the dy over dx, for example, in this case will be the product of 1/2 times negative 2x. I'm going to multiply those two on the side. So 1/2 multiplied by negative 2x. We can think of the 2x as being 2x over 1. And the way you multiply fractions is you go straight across. So negative 2x times 1 is just negative 2x. And then 2 times 1 is 2. But that's just the same thing as negative x. So I can rewrite that as negative x. So instead of the 1/2 multiplied with the negative 2x, now I just have negative x. And the other part, we just leave it alone. There's the plus sign that was in the middle earlier. I'll just leave it in the middle again. And now I gotta do the product of 1/3 with the 4. So what's the product of 1/3 and 4? So let me erase all this and just multiply 1/3 with 4. And again, I can think of this as being 4 over 1. And when you're multiplying fractions, you go straight across, top with top, bottom with bottom. So I can write 4 over 3 instead. And the base is 4x plus 3 raised to the power of negative 2/3. So that is technically the final answer. And again, how did I get the 4/3? I got it by multiplying the 1/3 with the 4. Now, we don't have any issues with negative powers in this problem, but if you wanted to rewrite the answer without negative exponents, then you can write it like negative x divided by the 6 minus x squared to the power of 1/2. So in other terms, I can bring this to the denominator as long as I switch the exponent from negative to positive. And also I can do the same thing on the second one. I can write 4 divided by 3, 4x plus 3 to the power of 2/3. I can do that as well. And so I can rewrite this base without the negative exponent as long as I bring it to the denominator and switch the exponent to positive. Now, which one should you use? Doesn't really matter. There are times when we prefer the first version. There are times when we prefer the second version. That's why I'm mentioning both of these. And so pick the one that you prefer and just use it. So what are we doing in example number 3? So example number 3 is going to show us that sometimes we can use the quotient rule and the chain rule. Sometimes we can avoid using one rule and use a different rule, basically, right? So you can avoid using the product rule, for instance, and use the chain rule. Or in this problem, we're going to see that we can avoid the quotient rule and do a chain rule, and we get the same result. Because the problem is the same, we should get the same result no matter how we find the derivative. But in this problem, we are going to start by assuming that there's a function called capital P of small t, which is 5 divided by 2t plus 1. And for part 1, they're saying find the derivative using the quotient rule. So I'm going to write down the p of t that I'm differentiating. It's 5 divided by 2t plus 1. And they're saying for this part of the problem, we want you to think of it like a quotient rule and find the derivative using the quotient rule. Now, technically, I don't have to use the quotient rule because the numerator in this problem does not have any variables. So, just keep that in the future in mind. I can avoid the quotient rule. The quotient rule is really necessary and required when you have variables on the numerator and variables on the denominator, and there's no other way to rewrite the problem or simplify the fraction. But in this case, I can rewrite the problem and avoid the quotient rule. But just to demonstrate that we can use either rule, the quotient or the chain rule, let's start by showing that you can get the derivative of this problem with the quotient rule. So first, for the quotient rule, I'm going to set up two functions, the f and the g function. Then I'll need to find their derivatives individually. And then I'll have to multiply some stuff and subtract along the way. This is basically the stuff we described in a previous section. The f function is the numerator, so that's 5. The g function is the denominator, which is 2t plus 1. Now, I need the derivative of each one of those guys. So the derivative of 5 is the f prime. The derivative of 5 is really 0. So that's the end there. And I need the derivative of 2t plus 1. The derivative of 2t plus 1 is just simply 2, because the derivative of 2t is 2 times 1, which is 2. And the derivative of 1 is really 0. So if I want the p prime of t, which is sometimes written like this, d capital P over dt. So remember, these notations are interchangeable. There's like 10 more other notations that I can use to describe the derivative, but I'll just stick to these two for now, just to keep reminding you that if you see apostrophe, that's the same thing as dp over dt, right? So just differentiate. This is a quotient rule, so we do low d high minus high d low, and then square the bottom, and off you go. That's the little song we kind of described before. But if you don't know the song, no big deal. Just multiply this corner with this corner, the 2t plus 1 with the 0, and then multiply the corner with the 2, with the other corner 5, and then square the denominator, and you're done, basically. So we'll start with the 0, multiply with the 2t plus 1. So 0 corner gets multiplied with 2t plus 1 corner. The rule tells me to put minus next, so that's this minus. I'm going to put it next. And then multiply the opposite corners. The 2 gets multiplied with 5. So remember, the 2 and the 5 go next. And then what am I supposed to do? Because it's a quotient rule, I'm supposed to square the bottom, and off I go. That's basically the end. Let's clean up this answer to make it look like the one I'm going to get on the next page when I do this problem with the quotient rule. So 0 times 2t plus 1 is just going to disappear, because 0 times anything is just really 0. And negative 2 times 5 is really just negative 10. And it's all divided by 2t plus 1, all to the power of 2. So that is the derivative of the function p. And we just used the quotient rule to get it, but like we will see in a second, this is not the only way. There's other ways to do this particular problem. And so what I'm going to do next in part 2 of the problem is find the same answer, and we'll come back to it and check that it's the same answer using the chain rule. Now keep in mind that the function p of t that we started with was 5 divided by 2t plus 1. And I mentioned earlier that there are no variables on the numerator. So I'm going to mention that and write it down. There are no variables. And so, because there are no variables, I can rewrite the original problem without a numerator and a denominator. I can rewrite it like this. I can write 5 times. Well, let's think about it for a second. The 2t plus 1 has a power 1, and currently it's in the denominator. Well, I can move it to the numerator, and all I have to do is really write down a negative exponent and with the 1 that was already there. And again, this is the same rule I used before on the previous page. If you have a base with a negative exponent, that just means it wants to be on the other side of the fraction. So if it's already negative on the numerator, just bring it to the denominator and make it positive, and vice versa. If it's already negative on the denominator, bring it to the numerator, it becomes positive. So in this problem, I had a base, 2t plus 1, which had an exponent of positive 1, but I decided it's more convenient to write it on the numerator. And in order to do that, all I have to do is just convert the 1 to be a negative 1 instead. So just give the power an extra minus sign, and you're good. So now that I have rewritten the problem, I can see that it looks like a base raised to some kind of exponent. So if I want the derivative, p prime of t, which is also known as dp over dt, then I can use this new rule that we learned. So I have 5 multiplied by 2t plus 1 to the power of negative 1. The 5 is just going to hang out and go for the ride. And we will just think about the derivative of 2t plus 1 to the power of negative 1. So if this was like a good old x there, I would drop the power down, then I would subtract 1 from the existing power. So there used to be a negative 1, and the rule tells me to subtract 1 always. Now, the base was not just a straight up x, it was actually 2t plus 1, so we need to write down 2t plus 1. And because it wasn't just the letter x or the letter t all by itself, it was a quantity with the 2t plus 1. What I need to do next is multiply this by the derivative of the inside. So derivative of 2t plus 1 is really in reality just simply 2. And that's basically the end. But let's clean it up to see that this solution is the same as the previous one we found on the previous page. So let's think about this. I have 5 being multiplied by negative 1, which is being multiplied by the parentheses, which is being multiplied by the 2. So let's collect all the numbers, 2, negative 1, and 5, and multiply them together. 5 times negative 1 is negative 5, times the 2 at the end is going to be negative 10. And finally, there's a negative 1 and another negative 1 in the exponent. Let's just write negative 2 instead. And to make it look exactly like the previous page, I'm going to remove the negative exponent. And how do I do that? I just rewrite the base that contains the negative exponent on the opposite side of the fraction. So it used to be on the numerator. Remember, it has the invisible 1 underneath it, so technically it's in the numerator. I can rewrite it on the denominator and write it with a positive exponent, and that's it. So this is, again, using the same rule that tells me what to do when I have a base with a negative exponent. Always write it on the opposite side of the fraction and switch the negative to a positive. And so we can see that we got negative 10 divided by 2t plus 1 squared, and that's exactly the same thing that we got on the previous page when we did the problem using the quotient rule. So why are we doing this? We're doing this because I want to demonstrate that it doesn't matter which rule you use. Sometimes one rule, in this case the quotient rule, may be worse to use than the chain rule. The chain rule may be easier or faster to apply. And by the way, once you have a lot of practice with the chain rule, this will be a piece of cake, whereas the quotient rule is always going to be a little bit more complicated to apply. Okay, so let's look at example 4. And again, we are going to find the derivative of this expression twice. One time we're going to use the chain rule, obviously, because we have some kind of base raised to the power of 2. So I'm going to use the general power rule. And the other time I'm going to find the derivative using the product rule, actually, because I can think of this 8x plus 5 raised to the power of 2 as 8x plus 5 multiplied by 8x plus 5. So I'll just separate the page into 2 halves, and I'll start by doing product rule on the first portion. So I'll show you how to find the answer using the product rule, and then we'll find the answer using the chain rule, and you'll be able to compare both of them and see that it doesn't matter which one you use, you get the same answer regardless. So we are given the expression y equal to 8x plus 5 squared. So in order to apply the product rule, I need to make it look like a product, and I could do that very easily by writing 8x plus 5 multiplied by another 8x plus 5. That's what it means to be raised to the power of 2. It just means write it twice. Okay, so now that I've written it twice, I can clearly see that there's a product in the middle. So this is a product. So therefore, let's go ahead and use the product rule. So the product rule tells me to find a function called f, find another function called g, and then find something for f prime and something called g prime. And I'm supposed to multiply those corners, f prime with g and g prime with f, but add along the way. Now, f is the initial part. It's the stuff you see before the multiplication sign. So in this case, I see 8x plus 5. So that is the f function. Okay, what about the g function? The g function is the stuff I see after the product sign. So in this problem, I'm seeing 8x plus 5 after the multiplication sign. So again, it happens to be the same, but that's okay. I'm going to record that the 8x plus 5 is the second part of the product. Now, I need the derivative of f to go on the side. So what's the derivative of 8x plus 5? Well, just simply 8, because 8 times 1 is 8, and the derivative of 5 is going to be 0. And in the same way, the derivative of 8x plus 5, which is the g this time, is going to be as well 8. So we found the derivatives, and now we are ready to find the derivative of the original problem, which we called y. So dy over dx, or y apostrophe or y prime. So what does the rule tell me to do? The rule basically says multiply 8 with 8x plus 5. So multiply those two corners. I'll go ahead and do that. 8 times 8x plus 5. Then the rule tells me to add, right? That's the part in the middle. And the rule tells me to multiply the opposite two corners. So again, 8 with 8x plus 5. And let me color code everything so you can see which parts are being which. So first, multiply the 8 in green with the 8x plus 5 in blue. Then multiply the 8 that I grayed out with the yellow 8x plus 5. Now, we can FOIL everything and add like terms and so on and so forth, but I'm not going to want to do that because I want you to compare and contrast with the second time I do this. So I'm going to do something here where I just add the 8 and the 8 together. So I can think of this as being 8 times some quantity plus 8 times the same quantity. So I have 8 quantity plus 8 quantity again, which means I have 16 of the same quantity. So my answer is just 16 times 8x plus 5. And just a reminder that the power really is 1 because there's nothing on the outside of the parentheses. So as you can see, it's not terribly difficult to do the problem using the product rule, but it turns out that there's a faster way called the chain rule. So again, I wanted to repeat the problem, and again, I am given the function y equal to 8x plus 5 with exponent 2. And I'm noticing that there's a base that has a power. So I'm going to apply the general power rule. The general power rule. So to apply the general power rule, to get the derivative, dy over dx, simply known as y prime, what do I do? So first, I pretend like there's a base, just like a normal x, and it's got power 2. So if I had like an x squared and I wanted to differentiate it, what would the answer be? Well, it would be 2 times x to the power of 2 minus 1. But unfortunately, the base was not just a normal x, it was 8x plus 5. So because it was 8x plus 5, not just a regular x, what I need to do next is take this base and find its derivative and multiply by it. What's the derivative of 8x plus 5? Well, just simply 8. So putting all together and simplifying it all, the y prime of this problem, the derivative, is going to be, well, 2 times 8 is 16. My base is 8x plus 5, and the exponent is going to be 2 minus 1, which is just simply 1. And so we are done with the question. And you can see that the two answers are exactly the same, but maybe one method is a lot better. And the method that's a lot better is the chain rule in this case. So It's better for you to use a chain rule, and it's good to realize that because you can save yourself a lot of times on exams and tests and get the answer much faster using that chain rule. Okay, so continuing with part 2 of the problem, we need the derivative again. And so again, here we have a product, but this time the product contains 7x minus 4 raised to the power of 3 and 2x plus 5 raised to the power of 4. So the first thing I'm going to notice here is that there is a product, which means I need to use the product rule. Because of the product inside the middle right there, I need to use the product rule. Now, the function y, or the expression, is 7x minus 4 raised to the power of 3 multiplied by 2x plus 5 raised to the power of 4. So what is f and what is g in this problem? So remember, the f is everything that comes before the multiplication sign. So in this problem, the f of x function is just 7x minus 4 raised to the power of 3. And the g function is everything that comes after the multiplication, which is 2x plus 5 raised to the power of 4. Now, according to the product rule, I need to know some things called f prime and g prime. Those are the derivatives of f and g, and I'm supposed to multiply the corners and add along the way. Now, the tricky part here is to find the derivative of f itself, I need to use the chain rule, because it looks like a base raised to the power of 3. So that's the tricky part of this problem. It's not that the product rule is being present, it's that the individual parts of the product rule, the f prime and the g prime, have to be differentiated using the chain rule. So what's the derivative of 7x minus 4 to the power of 3? Well, I bring the 3 down, then I subtract 1 from the 3, so it becomes 2. And I write the base 7x minus 4, but I need to multiply by the derivative of the inside. So the derivative of 7x minus 4 on the side is just simply 7. And if you can mentally imagine 3 times 7 is going to be 21 and write it down instead, that would be amazing. But for now, let's just keep it as is. Now, what about the derivative of 2x plus 5 to the power of 4? Again, I'm seeing some kind of base raised to an exponent. So the exponent comes down. Then I subtract 1 from the exponent. So it becomes 4 times the base, 2x plus 5 to the power of 3. But since my base did not contain just the regular good old x, I need its derivative to go next. What's the derivative of 2x plus 5? Well, just simply 2. And now it's time to put it all together. So the dy over dx, the derivative that we are searching for, also known as y prime, is going to be, according to the product rule, it's the product of this corner in yellow multiplied with the corner in blue. And then we're supposed to add along the way this time, because of the product rule, the corner in green multiplied by the corner in gray. So I'm going to write all that down and color code it so you can see where each part goes. And by the way, when I multiplied the corners with each other, I just decided to write, instead of 3 times 7, I decided to write 21 directly, and instead of 4 times 2, I decided to write 8 directly. That way we can skip a step. Now, this is technically the answer, and this is okay. You can leave it like this, but sometimes it's better to factor the problem a little bit if you can. So I'm going to spend maybe a couple of minutes here trying to factor this. But before I do that, let's make everything here just a little bit smaller so that everything can fit. Okay, to factor it, I'm going to look inside of the first box and ask what's common with what's inside the second box. And I'm seeing that there are some parentheses that keep on repeating. For example, the 7x minus 4 showed up here, and it showed up here as well. Now, the first box has 2 of them, the second box has 3 of them, so I can take out 2 of them and write it on the outside. In the same way, I see the 2x plus 5 repeating in this box, and I'm seeing 2x plus 5 repeating in that box. So I can also factor 2x plus 5. And how many can I remove? There's 4 repeating here, but only 3 there. So we can take only 3 and write it in front. So when we do that, what is going to be left in each box? Well, we took away all of these 2, 7x minus 4 squared. What's going to be left is 21, and we took 3 out of the 4 that were there from the 2x plus 5s. So there's going to be 2x plus 5 to the power of 1 left over. The plus sign goes next, so that's the plus that was in the middle. And let's see, we did not take any numbers out, so the 8 is going to remain. The 2x plus 5 is completely on the outside. All 3 of them were taken out and written in front, so no more 2x plus 5s on the inside. But for the 7x minus 4, we only took 2 to the outside, and we had 3 to begin with. So if we take away 2 from the 3, there's going to be an extra 1 left over to the power of 1 there. Now, the power 1s are not really necessary, so I'm just going to ignore the power 1s. And the last thing I have to do is really just FOIL the 21, or really I should say distribute the 21 over 2x and 5, and also do the same thing with the 8, multiply with the 7x and the 4, and add like terms. So let's just mentally do a little bit of math here. 21 times 2x will be 42x, and 21 times 5 is going to be 105. And next I have to multiply the 8 with the 7x, so that's going to give me 56x. Then finally multiply the 8 with the negative 4, that's going to be negative 32. So instead of wasting a whole line just to write that, I'll just do it right there in the middle and just wrap things up by adding 42x with 56x. So 42x and 56x are like terms. That means we're going to add them and they're going to give us 98x. And finally, the 105 and the 32 are like terms. They're both constants without x's. So when I add 105 and 32, I'm going to get 73 because 32 is technically negative. And so that is the end. I'm putting square brackets around this, but there's nothing wrong with putting parentheses if you prefer that notation. The bottom line is this is the derivative. And unfortunately for this problem, there is no other way to do this. I mean, you don't want to write 3 of those and 4 of those back to back and apply the product rule with basically 7 parentheses. That would be very, very difficult to do. So this is the only way, and this is the fastest way to do the problem. Now, we could have stopped on this line over here, but in general, these problems are not just going to be one-step problems. There are going to be questions coming later in the second part of the problem that require us to have the answer in the factored form. So this is why I'm spending a little bit of time on every problem to write the answer in a slightly better looking way, because later on we're going to take this answer that we put a box around and like set it equal to 0 and solve the problem or do something with it. So it's better to have it factored rather than in the original form with the unfactored answer. Now, like I said, it's important to recognize when product rules and quotient rules are necessary or when the chain rule can be used. So for this example 5, we're not going to find the answers. We're just going to say which rule can be applied and which rule is better to be applied. So it says compare or contrast how you would find the derivative of each one of these parts. So for example 5 part 1, I have the y equal to 3 divided by 2x plus 7. And it looks like a quotient rule should be used here, but really in reality, I can avoid a quotient rule. So I can avoid the quotient rule and use the chain rule instead. So how would I do that? So use the chain rule. I can avoid the quotient rule and use the chain rule because, first of all, there's no variables there. So there is no x variable, no x variable. And so that's how I know that it's possible to avoid the quotient rule. The quotient rule is really required when you have x's on the numerator, x's in the denominator, and you cannot simplify the expression. But I can avoid the quotient rule by rewriting the problem like 3 times 2x plus 7 to the exponent negative 1. So originally, the problem had 2x plus 7 to the power of 1 on the denominator. I could bring it to the numerator and make it negative and apply the chain rule instead. So that's how I can avoid the quotient rule, which is usually the most complicated rule in our course, and instead use the chain rule, which is slightly less complicated and better. Now, for the second part, we have y equal to 3x over 2x plus 7. Here, there is no way to avoid the quotient rule. We have variables on the numerator, we have variables on the denominator, and they cannot be reduced. They cannot be divided out or anything. So this problem has variables on both the numerator and denominator, so we must use the quotient rule. So I'm writing must use the quotient rule. And again, that's because both my numerator and denominator contain variables and they cannot be reduced or avoided. So I must use the quotient rule for this problem. Okay, so for part 3, we have the function which is 2x plus 7 divided by 3. So again, it looks like it could be a fraction, so it looks like I should use the quotient rule, but the denominator has no variable. So there is no x variable here, no x variable. And so when the numerator or denominator is missing an x variable, there's always a way to rewrite the problem and avoid the quotient rule. So in this case, I can rewrite the problem like this. I can write it as 2x over 3 plus 7 over 3. I can give each factor in the numerator its own denominator. So the 2x gets its own denominator, the 7 gets its own denominator. They both will have denominator 3. And in reality, I can write it like this, 2/3 x plus 7/3. And now you can completely see that this problem requires just a simple derivative rule, and the derivative will be y prime equal to 2/3, because the derivative of x is 1, and so 2/3 times 1 is just 2/3, and the derivative of 7/3 is just really 0, and we don't even need to write it down. So how much faster would it be to find the derivative this way, rather than doing the quotient rule with the setup f and g, and then you got to multiply f g prime minus g prime f, and then square the denominator, and off you go. It's a lot of work to do the problem using the quotient rule. So we can avoid a quotient rule and use the basic power rules to find the solution here. Okay, so let's continue along. And in example 6, we're basically told to find the equation of a tangent line. We've dealt with these types of problems in the past. This is not the first time we see one of these things. And so the process is basically always very similar. When you hear the words find, equation, and line in the same sentence, you will always begin with y minus y1 equal to m times x minus x1. So that's how you find the equation of any line in general. This is known as the the point slope formula. So point slope formula. So this formula requires a few things from you. It requires an x1, and that's the number that's usually given in the problem. And I'm always choosing 1 just for simplicity, but the number could be anything. It could be 4, it could be 5, it could be -10, it could be 2, just depends on the problem. I'm using 1 because it's simple. And it requires a y1 from you, and also it requires an m. So those are the 3 things that you need to put into the formula. And once you put them into the formula, you get the solution of your problem. You get basically the equation of the tangent line to the function that you are interested in. Now, the important thing to remember is that to get m, you need to find it by putting the x1 into the derivative. So you put the 1 into the f prime, into the function's derivative. And the other important thing to remember is that to get y1, you put the x1 into the regular function, not the f prime. You just use the regular f of x. So basically, we have to plug 1 into 2 different things, into the function and into the derivative of the function. So remember, the function is f of x equal to 4 divided by 5 minus 3x, all of it squared. So that's the original function f of x, and if I plug 1 into it, what do I get? So if I plug 1 into it, I'm basically searching for y1, and what I would get is 4 divided by 5 minus 3 times 1, everybody squared. And that's the same thing like 4 over 5 minus 3 squared. But 5 minus 3 is really 2, and 2 squared is really 4. And 4 over 4 is really 1. So now I know that the y1 is the number 1. So I know that this guy is equal to 1 now. So that's half the battle. The remaining thing is to find m, which is the derivative with the number 1 plugged into the derivative. So to find m, I'll need the derivative. Now remember, the function itself is 4 over 5 minus 3x to the power of 2. And the numerator does not have a variable. So I can rewrite the f as 4 multiplied by 5 minus 3x raised to the power of negative 2 instead. So I can basically take the exponent 2 and make it negative and just put the base in the numerator. And so why would I want this? Well, I want this because now it's going to be easy to find the f prime. So let's look for f prime over here. So first we found y1. Let's look for the f prime next and then plug in 1 in it. So the 4 is just going to hang out and go for the ride. The base is 5 minus 3x with the exponent negative 2. So I'm looking over here. The base is 5 minus 3x and the power is negative 2. So the negative 2 comes down. The base stays there for a moment, and we subtract 1 from the existing power. So the existing power used to be negative 2, and I'm subtracting negative 1. The total of negative 2 minus 1 is just negative 3. Let's write that instead. But unfortunately, the base was not regular old x, so now I need the derivative of the inside to go next. The derivative of 5 minus 3x is just simply negative 3. So we write it next to it, and that is the derivative of f of x. Looks kind of complicated, but remember we're going to plug a number into it, and so it really doesn't matter what complication it's got. The calculator can do the rest. So to find m, I need to take this derivative and put 1 into it. So take the 1 that is in the problem, that was given in the question, and put it into the x term. So I'm going to get 4 times negative 2 with 5 minus 3 times 1, all raised to the power of negative 3 multiplied by negative 3 again. And again, the way I'm getting this is by putting 1 into the x. And that's because the problem asked me to plug in the 1. They said they wanted the equation of a tangent line when x is equal to 1. Now, you can put all this into your calculator and get m, or you can do it by hand. Regardless of how you find it, the answer that you should see on your screen is just simply 3. So m is now equal to 3, and so we know that this guy over here is now equal to 3. So now that we have all the numbers that we need, and it took a little bit of time to find them, we can finalize the answer. We can say y minus 1 is equal to 3 times x minus x1, which is 1 as well. So remember, this one is the number that was given in the problem and the question. This one is the number 1 from the question plugged into the regular function f of x. And finally, the 3 is the number we got when we put 1 into the derivative. And the tricky part in this problem was getting the derivative, and it required the chain rule, the brand new rule that we're learning. In any case, the answer is going to be 3x minus 3, and I need to bring this negative 1 over, so it's going to be plus 1. So the answer is 3x minus 2, and we are now finished with the problem. The last two problems in the section are application problems, so let's go ahead and read example 7 and work on it together. This is a business application that says, suppose we are given a total revenue function called r of x, and you can read it there, and a total cost function called c of x, where x is the number of items produced and sold, and r and c are both measured in thousands of dollars. In part 1, they want me to find the profit equation, or the profit function p of x. So remember, p of x in business is just the revenue minus the cost. And what I have to be careful about is that my cost equation has multiple parts, and it comes after a minus sign, so make sure you put parentheses or brackets around everybody. So anyway, in this problem, the r of x is 800 times the square root of x squared plus 0.1x all of it inside the square root. So that's the revenue equation or the revenue function. And then I'm supposed to subtract. This is something you have to know. Nobody's going to tell you this on an exam or a quiz. You have to subtract the cost function. And the cost function has multiple parts. So again, make sure you use some brackets or parentheses. But in any case, this is x squared plus 1 to the power of 1/3, all multiplied by the 2100, and then plus 500 at the end. Now, to be consistent, I'm going to rewrite the answer first, avoiding the brackets. I'm going to remove them. So that means I'm going to have to distribute the minus sign to the second two terms. And also, I want everybody to look like a base with an exponent, kind of like the x squared plus 1 to the power of 1/3. So if I have to find derivatives later on, which I probably have to do, it'll be ready to go. So rewriting the answer in a simpler version, we can write 800 times x squared plus 0.1x, all raised to the power of 1/2. So where did the 1/2 come from? There's an invisible 1 and there's an invisible 2, and you can rewrite it as power 1/2, again using the n rule to the power of m. So if I have nth root of a to the power of m, that's the same thing as a to the m divided by n. So that's the rule that allows me to convert from radical to power or vice versa. Then I have to give the negative to the 2100, x squared plus 1 with power 1/3. Then finally, the negative goes to the 500. And that's my profit equation, all nice and ready for any derivatives that I might need to find. Speaking of which, in part 2 it says find the rate at which the profit is changing when X items have been produced and sold. So rate just means derivative, and they're talking about the derivative of the profit function. So in part 2 of this problem, I'm going to be searching for the p prime of x. We can also call it d capital P divided by dx. So regardless of what notation is used, that's the derivative, that's the rate at which the profit is changing. Now, in both of these instances, there's 800 multiplied by some stuff and 2100 multiplied by some stuff. So we're going to ignore the 800 for a second and just worry about the x squared plus 1 with its power and so on and so forth. So there's a base raised to an exponent. So we're going to use the general power rule, drop the exponent down, leave the base alone for a second, and subtract 1 from the existing exponent. So it used to be 1/2, and I'm subtracting 1. The total is just really going to be negative 1/2. Let's just write that instead. And I am expected to multiply by the derivative of the inside. Derivative of x squared plus 0.1x will be 2x plus 0.1. So that's the derivative of the inside there. And that's the end of the first part up until this minus sign. So this minus sign is next. And again, the 2100 or the 2100 will just hang out, and we will differentiate x squared plus 1 to the power of 1/3. And so this is again a base raised to an exponent. So we drop the base, we drop the exponent, we write down the base x squared plus 1, and we subtract 1 from the existing power. But 1/3 minus 1 is really just negative 2/3, so I'll write that instead to avoid writing extra lines. And again, my base here is x squared plus 1. I need its derivative next. So what's the derivative of x squared plus 1? It will be just simply 2x, because the derivative of 1 is really 0, and that's the end of that second part. And finally, we have one more number to worry about. There's the negative, and the derivative of 500 is really 0, but you know what? Let's just not write it down. So this is it. Now, my derivative looks kind of crappy, and I'm going to spend a little bit of time here to make it look as pretty as possible. And what I'm going to do is really multiply the 800 with the 1/2, and that's it for the first part. There's not really much else I can do. And by the way, 800 multiplied by half is just really 400. If you like, we can avoid the negative exponents by writing down a fraction and putting x squared plus 0.1x in the denominator and giving it a positive exponent. So instead of having the negative 1/2, I can now have a positive 1/2. And the last thing that remains is the 2x plus 1 with the 2x plus 0.1. It technically has a 1 underneath it, so we can write it in the numerator. And so that's this whole thing simplified. The minus that was in the middle, that's this minus right here. And again, I've got 2100 and I've got 1/3, and then I've got a 2 at the end. So I can multiply those three numbers and write a simpler version. 2100 multiplied by 1/3 is going to be 700 because it's technically 2100 divided by 3, so 700. And 700 times 2 will be 1400. There's an extra x at the end that has a positive exponent, so I'm going to put it next to the 1400. And the last thing I'm going to do here is write the base x squared plus 1 on the denominator with power 2/3 instead of negative 2/3. So it used to be negative on the numerator. I write it on the denominator with a positive exponent. So that is it. That is my derivative with the prettiest shape it can be in, basically. Now for the last part of this problem, we're told to suppose that 100 items are produced and sold, and we're being asked to find the profit and the rate at which the profit is changing. They want us to also attach the units to our answers. So what are they asking for? Basically, they're saying find the profit. That means we need to plug the 100 into the profit equation to get the answer there. And also they want us to find the rate at which the profit is changing. The rate, remember, is the derivative. So that means they want us to put 100 into the p prime that we already found. So remember, the p and the p prime are these functions that we just found earlier in the problem, and we have to replace the x's in there with 100. So let's begin with the p of x. So I'm just going to grab it from the top of the problem and bring it down, and also replace all the x's with 100 to see what I get. So x is 100, so we're going to replace it with 100 everywhere, and we can put this in our calculator to get the final answer. We'll do this on the main screen of the calculator. So we'll start by typing in the 800, and then we'll put some parentheses with the 100 squared, because that used to be an x, plus 0.1 times 100. And we're going to close all this and raise it to the power of 1/2. Now be careful. The power needs to have parentheses around it. Otherwise, the calculator will understand that you're raising it to the power of 1 and then dividing everybody by 2. That's not what we want. We want the power to be 1/2. So that's why I'm going to put parentheses around the power. Then minus the 2100 multiplied by, again, 100 squared plus 1. And again, it's the same story here with the power. We need to put the power inside parentheses. So 1/3 gets the parentheses minus 500. So the final answer is 34,295 point something 35346. So they didn't tell me which decimal they want me to round to. So I'm just going to write down 34,295. 34,295. Now remember, the unit here in this problem is in thousands of dollars for cost and revenue, and the profit is going to be measured in the same units. So this is in thousands of dollars. So in reality, what this means is that if I want to know the profit of 100, then really I should multiply the answer that I got by 1,000. So 34,295, and we're going to add 3 zeros. So this is about 34,295,000. Okay, so that's the profit. So we're done with the first part of the problem, and now we want the derivative, or the rate at which the profit is changing. So the p prime of 100. So again, the way it's going to work is I'm going to grab the answer that I got from part 2 for the p prime and just copy it to my bottom and replace all the x's with 100. So there's a few places where x shows up here, so we're going to be a little bit careful. So there's x's on the numerator and in the denominator, and I'm just recording it so we can see what we're going to need to type into the calculator. So this is what it should look like. So let's go to our calculator and plug this in. So we begin by putting the 400 multiplied by the 2 times 100. plus the 0.1. That's the numerator of the first fraction, and the denominator consists of the 100 being squared plus 0.1 times 100, and all that is raised to the power of 1/2. Again, the same story as before. Make sure you use parentheses around the exponent. So that's the end of the first fraction, and let's put the second fraction directly next to it. So we're going to subtract 1400 multiplied by 100, all divided by, my denominator contains multiple terms, so parentheses 100 squared plus 1, all raised to the power of 2/3. And in this case, I'm getting 498.399. So again, they didn't tell me what decimal to round to, so I'll just round it down to 498. So the answer will be, let's put it in black, the answer will be 498. And this is the rate unit, so it's going to be thousands of dollars per item. And with that, we are done with this example. So the last part of this section deals with compound interest. This is a famous formula that we will discuss later on a little bit more in detail. But for now, we're told that if $5,000 is invested at an interest rate R, and it's compounded quarterly, so meaning you're paid out the interest every quarter, so every 3 months, in 8 years, the amount that you've invested will grow to an amount that we call A, given by the formula that we see in the middle of the page. So 5,000 times 1 plus R over 4 to the power of 32. So part 1 of the problem is pretty straightforward. They just want us to write the rate of change, dA over dr. So in other terms, that what they're saying is they want the derivative of that expression or that function. So in my problem, I am given that A is 5,000 times 1 plus R over 4, all to the power of 32, and I'm being asked for the derivative of A with respect to the letter R. And it makes sense because R is the variable in this problem. That's why we're writing dA over dr. This is also known as a prime, but in this case, the notation dA over dr is a little bit more useful because it tells me that the independent variable is R and the dependent variable is A. In any case, the A prime of R, meaning the function that I'm looking for, is going to have the 5,000 hanging out in front. It's not going to change because it's just a constant being multiplied by a bunch of stuff containing the variable R. So for this part over here, we will need to use the new chain rule that we discussed in earlier parts of the section. So the way it's going to work is we bring the power down, then we write 1 plus R over 4, and we will take the original power 32 and we will subtract 1. And by the way, 32 minus 1 is really 31, so let's just write that instead. And we're not done yet because the base in this problem is not just the letter R, it's got 1 plus R over 4. So we need the derivative of it to go on the side. And as we know, the derivative of 1 is 0, and the derivative of R over 4, we can ignore the 4. Derivative of R is 1, so it's just 1/4. That's the derivative of the inside. So now we can finally finish the problem and say that A prime, in other terms, the dA over dr that we're looking for, is equal to the product of 5,000 times 32 times 1/4. We can use our calculator to get the number there. The calculator should say 40,000 when you plug those numbers in, and the parentheses contains 1 plus R over 4 to the power of 31. That remains unchanged, and that is the derivative of the expression in the question. So remember, for this problem, there's no other way to do it. I mean, you can try to do the product rule 32 times because of the power 32, but that's ridiculous. It will take forever to get the answer. Whereas doing it with the chain rule or the general power rule in this case, it is much easier. So now that we have the derivative, they want me to do a few things with it. They want me to evaluate this expression with 3 different numbers plugged in. First, they want me to plug in 5% for R, then 10% for R, then finally 20% for R. So They want us to find the derivative of dA over dr, and they want me to plug in r equal to 5%. So I'm going to start using this new notation where I write the dA over dr slash, like a vertical line, and then r equals to 5%. This notation just means that I'm about to plug the 5% in place of r inside the function that we're calling dA over dr, or in this case, the derivative. So that's a notation that I'm going to start using from now on for certain problems. So that's what I wanted to mention it here. And so this is really just 40,000 times 1 plus r is supposed to be 5%. And 5% is 0.05, and divided by 4 all to the power of 31. So that r is going to go right there. In the same way, we're going to do the same thing for the 10% and again for the 20%. So if I plug in 10% for the r, then I would get 40,000 times 1 plus 10% is 0.10 to divide by 4 to the power of 31. So again, what I did here is I replaced r, 10%, with 0.10. And finally, for the dA over dr with the r at 20%, the interest rate at 20%, I'm going to get a similar expression with 40,000 times 1 plus 0.2, all divided by 4 to the power of 31. So I wanted to write all of them down first before we go and look at how to plug them into the calculator. But now that we have all these numbers, we can go and visit our calculator and see what the answers for each one of these will be. So on the main calculator screen, I'm just going to type in 40,000 times the 1 plus the 0.05 divided by 4 to the power of 31, and that will give me the first answer. And if I want to do this quickly again without having to type everything all over again, I'm just going to click second and enter. And when you do that, it just brings back the last entry that I typed in. So instead of typing everything all over again, I'm just going to go back with my arrow keys and replace 0.05 with 0.10. Hit enter one more time, and I get the new value for 10% rate of interest. And finally, again, I'm going to click second, enter one more time, and change the 10% to 20%. So this is a quick, efficient way of getting all the numbers without having to type everything every single time.